And the first thing we are going to do today is, if I give you this logarithmic equation here, can you rewrite this so that it is the sum of different logarithms? So expand this out as much as you can into different logarithms. This has to do with the last thing that we covered yesterday, so if you need to look back at your notes, you can. And I will give you some time to work on this. I would like row 5, person 1. There we go. Simple as that. So yesterday I don't think we necessarily put a term to this or a name to this concept. But this concept is called the product property of logarithms. So today, looking forward, you can either download the notes that start with this slide. It is today's date, 12/4. Or you can just continue on a blank notability sheet. Either one will work for today. So if you're already on a blank notability sheet, just continue using it. Otherwise, you can get to this slide in today's notes. Kind of look forward. You will be having another lab shortly. Not today, but you'll be having another lab shortly. This lab has to do with M&Ms, which means you'll probably have a good chance of eating them once you're done with them. We will not talk about it just yet, because I do want to get through a bit more material today than usual. But once you are on either a blank notability document or on today's slides, could you flip your iPad towards me and keep it flipped towards me so I can see that we have everybody. I'm going to wait until I see everybody has flipped either a blank notability document or a slides towards me. So I'm waiting on 2 people. Okay, awesome. Right now, we aren't necessarily using the notes, but we will get to those notes. So if you just want to pull up a blank page. Yesterday we learned about the product property. Today we are going to learn about 2 other properties of logs. The next one is called the quotient property. And if we're looking at the quotient property, product property was for multiplication, quotient property is for division. If I have a log of some base, so base b, and in my parentheses I have x divided by y. So some number x divided by some number y. If I think about the product property, we said that our product property translated from the product to addition. So if we're starting with division, what do you think it will translate to? Subtraction. If you said subtraction, your instincts are right. If we have log base b of x divided by y, that'll just tell us that you will have log base b of x minus log base b of y. The other property that we want to learn today, it's not called a property, but it is called the product, I apologize. It is called the power rule. And for the power rule, let me pose a question. If I have log base 2 of 8, Yesterday we said we can rewrite log base 2 of 8 as log base 2 with a base of 2 in our argument. And then what was the power that we needed? So we said log base 2 of 2 to the third power is equivalent to log base 2 of 8. And we said that if we were solving this for x, we could cross off this part here, and all we have left is just that 3, so 3 equals x. Except if you look at that, that doesn't really make mathematical sense. How could you cross out this, and you still have an exponent, but your exponent is your answer? The reason why this works is because of the power law, or the power rule, excuse me. For the power rule, all it tells us is that if you have this exponent here, if you have any kind of exponent here in your argument, you can take this exponent and you can just put it in front of your logarithm. So we could rewrite this as 3 times log base 2 of 2. And if you have log base 2 of 2, what does log base 2 of 2 equal? Just 1. So if log base 2 of 2 equals 1, this is the same thing as 3 times 1, which is just 3. So we find that 3 equals x. And that is the mathematical reason why we can just cross off. If you have a base here and a base in your argument that are the same, that's why you can just cross it off and take your exponent. Is because you can rewrite your exponent in front of your logarithm. So if we had log base 5 of 625, you could solve this many different ways. I would like you to solve this using the power rule. I'll give you a few moments. Try and think about how you can solve this using the power rule while I pause our recording. Calling on somebody using the dice of destiny. Row 5, person 6, to be Quinn.
Want me to do the thing? Yeah. Okay. So, 6.5 is the same as 5 to the 4th power. Then becomes 1 base 5, 5 to the 4th, and get rid of 5, 4.
Right. So we know that 625 is the same thing as 5 to the 4th, as Quinn has told us. And so if we use the power rule, that just takes our 4 and moves it in front of our logarithm here. And we know that log base 5 of 5 is the same thing as 1. So this is 4 times 1. So you will get that x is equal to 4. Okay. Today, what we are doing with these laws, we'll be using these laws, but we'll be using these laws in ways that you might not realize you're using them at first glance. However, if we just look at this first one here, we're going to look at this first problem, and what we are doing now is before we had some kind of exponent, and it was equal to some number, or we had some kind of exponent and it was equal to x, and all we have to do is solve our exponent. Now our problem is that we have some kind of exponential function equal to another exponential function, and we need to solve for x still. So if we look at this first one here, if you think back to exponent rules, what needs to be true about our bases in order for us to use exponent rules? Our bases do need to be the same. So if we look, we have a 4 here and we have a 2 here. Could we get one of those to become the other? You probably could. So if you could, right now, take a few moments, get them to be the same base, and then try and solve for x. pause our recording while we solve. I would like to call on row 2, person 1. Ryan, what did you change your bases to? So we're looking at our bases here, 4 and 2. And we want to change it either to 4 or to 2. Which one would you like to do? Change it to 4? Okay, so if we're changing to 4, then we're going to keep this first one the same. And we want to change this one here to 4, right? If we want to change to 4, you start with a 2. And to get to 4, we need to put it to the power of 2. Except this 2 right here that we just put in, that came out of nowhere, right? If it came out of nowhere, that means that we changed our equation just then, which means we need to change it back as well. So if we changed it by putting it to the power of 2, then to change it back, you would also have to put it to the power of 1/2. And then you still have the power of 3x minus 1 in your exponent. So once we do that, we'll have 4 to the power of x is equal to 4 times the 1/2 distributed in. So that'll be to the power of 3/2 x minus 1/2. And if we have the same base now, what can we do with our exponents? We have the same base. What can you do with your exponents? Turn and talk to your table partner. Okay. I'm hearing a lot of people who know what they're doing. Who wants to volunteer what they know what to do? Would you like to? Okay. So we can take our exponents and we can set them equal to each other now. Okay. Good to know. If we set these equal to each other, it just becomes some algebraic equation that you can solve. So if we were to solve this out, you would end up with 1/2 x is equal to 1/2, or x is equal to 1. Show of hands, who did this by changing it to a base of 4? Who did this by changing it to a base of 2? So you could change this to a base of 4, like we did. You could also change this to a base of 2 by keeping the right side the same. And on our left side, if we want a base of 2, what do we need to do? So here we had 2, and we need to make sure that we kept that as 4. So 4 is the same thing as 2 to the second power, and you still have your x outside. So this would be equivalent to 2 to the power of 2x is equal to 2 to the 3x minus 1. And if we do the same process of setting our exponents equal to each other, you will end up using algebra with x equals 1 as well. You can do it either way. Either way is fine. If there's one way that works better for you, please, by all means, go ahead. Okay. I need to erase this. Well, let's see. Can I see what it says over there? Okay, I'm going to use another page, but we are going to do this problem here that I have erased. We're going to do this problem, and I'm just going to write that further down on our page here. And if you look at this problem, you quickly run into a problem. Can we change these bases to be similar to each other? I don't know. I can't figure out a way to get 2 to go into 5 using powers. So our problem problem here is we don't have a way to change our bases, so we can't just use exponential rules, which is where logarithms come in. If you have two bases where you know that you can't get them to be the same, what you can do is, our entire goal here is we want to solve for x, so we need to get these exponents down, right? If we want to get them down, if I take the natural log of both sides, so I just say, okay, whatever I have on the left side, I'm just going to say the natural log, and then put whatever that is on the left side into the natural log. And then I'm going to do the same thing on the right-hand side and say the natural log, and then whatever's on my right side, I'm going to put in my natural log. And the reason why I want to use these logarithms, if I have this 5 to the 5x inside of my natural log, and I need to do something with my exponent, what can I do with my exponent? If you think about the power rule that we just learned, can't you just move it out? So on both of my sides, I can take my exponent and pull it out, so that I can rewrite this as 5x times the natural log of 5 is equal to x plus 7, natural log of 2. So now I don't have to worry about exponents anymore. Now all I have to do is just worry about solving for x. If I want to solve for x, what do you think would be a good next step? What specifically would you like to divide? So if we want to get all of our x terms all on one side, what would you like to divide first? Because we can divide either of these. I'm just going to divide by this. So I'm dividing by x plus 7 on both sides. And if I divide by x plus 7 on both sides, that gets rid of this here. But I still need x by itself. If I need x by itself, my problem now is I have this natural log of 5 that's still here. And natural log of 5 has nothing to do with x. So let's divide that out. So if I divide by the natural log of 5 on both sides, then this cancels out, and I don't have it anymore. And all I'm left with now is all of my x terms are on this side, and all of my non-x terms are on this side. And if I look at the natural log of 2 divided by the natural log of 5, is that a variable or is that a number? Can you solve for this on your calculator? You can't, so it's just a number. So this is some kind of number. So all we have now is we have some values of x are equal to a number. So let's figure out what that number is. If you have a graphing calculator, pull out your graphing calculator. Otherwise, you should be able to do this just on your iPad's calculator. And once somebody has the natural log of 2 divided by the natural log of 5, let me know. What you get, Olivia? 0.4306. Okay, I'm gonna go with 431. Did somebody else also get this and can agree? Awesome. So now we have some number on our right-hand side, and we have this equation of 5x divided by x plus 7 on the left-hand side. But we still need to solve for a single x. Well, now that we've got just a number on our right-hand side, let's put our x plus 7 here back on that side. If we do that, we cross this out, and all we're left with again on our left side is 5x. And over here on the right, we have 0.431 times x plus 7. So now that we have this, because this is a number here, we can take our number and we can distribute our number to both parts of our x plus 7 quantity. So we have 5x is equal to 0.431x plus 0.431 times 7, whatever that value will be. And from here, it's just basic algebra. Get all your x terms on one side. Solve for your x only. So take a few seconds, finish solving this out, and share with each other what you're getting for your x value. I will pause while we do this. We've had a little bit of time to work on this. So row 5, person 3. Could you tell us what you ended up getting for your x value? So 0.66. You may have gotten something that's a little bit different than this. As in, you might have gotten something that was like x equals 0.68, or 6.7, or 6.5. And that has to do with rounding. When you are using logarithms, the hard part about this is that we have numbers that aren't nice numbers when we're taking these logarithms. And so when you're writing down 0.431, you can write that down as your rounded number, but on your calculator, try not to round. We talked about how you can use that answer button and how you can use the answer button so that you can get previous numbers. So really try and use that so that you aren't rounding on your calculator until the very end. Okay. The other thing that I wanted to talk about is at the very beginning here, I used the natural log. And I've gotten a lot of questions from people saying, wait, why are we using the natural log here? Why don't we just use the log? Because it's the same thing, right? The reason why I like to use the natural log is because if you have a case where you have something like this problem here, but, for example, you have, instead of 5, you have e to the 5x equal to e to the x plus 7. This problem will not work if you just use the basic logarithm. This problem will only work if you're using the natural log. And it actually makes it a lot easier to use the natural log. But the problem that we were doing before, where it has 5 to the 5x, if you use the natural log, or if you use the logarithm of some base, it doesn't care. And so I want to make your lives easier and not give you, okay, you have to do this in this case, and you have to do this in this case. So overall, I would just say if you have to use some kind of logarithm in order to get the exponents out, always use the natural log so that you don't have to worry about, okay, does it have an e in it? If it does, I have to use the natural log. If I don't, then I can just use the log. So it makes it a lot easier for you to just keep it straight in your head where it is, if I want to simplify this and get the exponents out, just always use natural log, regardless of what your base is. Does that make sense to people? It was a good question. I'm glad people asked. The last thing I would like to do, actually before we do this, I would like to give you a practice problem on your own. I would like you to try this number, 27. And it's on this page with a rock formation. And I was told last period that rock formations like this are called Karen. Does anyone know if that's true? A kid from last period told me this. I will not disclose names, though. rocks that are stacked on top of each other. I just call them the rocks from Moana. I don't know how else to describe them. But
go on hikes, that's what fingers my
it's called Karen. Interesting. The things I learned from teaching. So if you could solve problem 27, we're solving for x again. Try this one on your own. I will pause while you're doing so. I have rewritten the problem further below so that we can see it a little bit more clearly. But from this step here, we have to figure out how we can solve for x. So is there someone who would like to volunteer to give us the first step? And it's the easiest step. I would volunteer now. Okay, Greta, why don't you start us off?
Multiply by ln.
We want, yes, so we want to take both of our sides. We want to say the natural log of 7 to the power of 3 plus 7x is equal to the natural log of 3 to the power of 4 minus 2x. And if we have taken the natural log of both sides, why is that so important to us? Row 6, person 3. Can you tell us the next step, which makes our natural log so important? Exactly. Once we have the natural log, we can use our power rule. And the power rule tells us that we can take our exponent and move it outside. So we're left with 3 plus 7x times the natural log of 7 is equal to 4 minus 2x times the natural log of 3. And from here, row 4, person 2. Bobby, what was your next step?
I divided the side by natural log of 3 and 7 plus 3.
So you divided both sides by 3 plus 7x and by the natural log of 3?
Yep.
Sorry about the red writing on red writing. But if we look at this, that means that we have canceled this component here out, and we have canceled this part here out. And if we rewrite this here, we are left with the natural log of 7 divided by the natural log of 3, which is equal to 4 minus 2x over 3 plus 7x. Okay? For our next step here, row 5, person 5, would be Becca.
So we've simplified the natural log of 3 to 0.565.
So we have calculated the natural log of 7 divided by the natural log of 3, and we got this decimal here. And if we have this decimal, now we want to figure out what to do next. So row 2, person 3. You might have divided it log of, or natural log of 3 divided by the natural log of 7. Yes.
So we wouldn't come out with the right answer unless 4 minus 2x is in the denominator using that answer, because that answer is log of 3 divided by 1.
This one here?
Yes, not log of 7.
That is very true. Okay, so this was for if you had the natural log of 3 divided by the natural log of 7. So then here should be 1.771. I apologize, I did not catch that. So if you had the natural log of 3 divided by the natural log of 7, you'll be getting a different decimal here. You'll be getting the decimal that we just had written there. But instead, since we have the natural log of 7 divided by the natural log of 3, this is our decimal now. And so from here, if we just want to solve for x, our problem is we have an x in our denominator. So let's multiply both sides by 3 plus 7x once again. And if we do that, we will end up with, I did this last period too. We will end up with 3 plus 7x times 1.771 on the left-hand side, which we can distribute this number in. So if we distribute this number in, we'll have 3 times 1.771 plus 7x times 1.771. And on our right side, we will just be left with 4 minus 2x. So all I did here was I took my 1.771 and I distributed it to each of my terms. If you look at this, from here, it's basically just manipulate algebraically in order to get to our x value. So could I have somebody volunteer and give me what they got for their x value? And the x value should be the same for everyone, regardless of how you solve. Yes. Negative 0.091. Confirmation? Who else got this? Awesome. Okay. We have about 10 minutes left. I would like to go over one short example that looks like it's a really hard exponential problem, but it's really not. And that problem is, let's see, it's a little bit far back up. I realize that we're kind of jumping around today, which is why I said a blank notability document would serve our purposes today. But if we want to look at this page, it starts with odd solving part 1. And we want to look at this first one here. And you can get very easily intimidated by this because it has that exponential term in there that we were talking about earlier. And for this exponential term, our problem here is, our first instinct is you want to take the natural log of both sides, right? Except if you have this plus in the middle, that taking the natural log of both sides isn't really going to help you. So now you're left with the problem of, okay, regardless of what I do, I'm going to have 2 terms on both sides, on one of my sides. What do I do now? Let's think about it this way instead, though. What if I wrote this in terms of e to the x? If I wrote this first term here in terms of e to the x, what power does e to the x need to be to? Just to the second. So all I did was I just factored out that power of 2. And then if I look at my second term here, and I just want to separate out the e to the x, that's just 5 times e to the x. And the last thing that I want to do is, if I have an equation, and I'm trying to solve for x, what is typically always true of the right-hand side of my equation? It's equal to 0. So I'm going to add 6 to both sides so that this side, the right-hand side, is equal to 0. So now I've got an equation, and I've pulled out of this e to the x power. What if now, instead of e to the x, I cross it off and I just wrote x? And wherever I saw an e to the x, I cross it off and just wrote x. Then, if I rewrite this, do you know how to solve that equation? Whoa. Okay, so all we have to do is just factor this. If we factor this, what are our 2 factors? They'll both be positive. They will both be positive, and it will be 2 and 3. So we have positive 2, positive 3 to complete our factors here. And from our factors, then if we write this out into our two cases, we'll have x plus 2 is equal to 0, or we have x plus 3 is equal to 0. Except back up here, we didn't start with x. We started with e to the x, and then we replaced it with x. So now that we've kind of figured out a few things, let's replace it back with e to the x. So now down here, wherever I see an x, I'm going to write e to the x. And if I just solve this out algebraically, that means I have e to the x is equal to negative 2, and e to the x is equal to negative 3. And if I'm trying to get x out of the exponent, what should my next step be? Exactly. If you ever want to get something out of the exponent, you always want to head towards the logarithms or the natural logs. So we have natural log of e to the x is equal to the natural log of negative 2. And over here we have the natural log of e to the x is equal to the natural log of negative 3. Who can remind me, if I wanted to write the natural log back as a logarithm using our regular log, what was the base of the natural log? The base was e. So if right here I have log base e of e to the x, what can I do? Just take this. I can cancel off that part, right? And all I'm left with on my left side is just the x. So whenever you see that you have a natural log and an e, natural log and e can cancel out just like we did if our bases matched, because natural log and e, their bases do match. So we can cancel those out, and once we cancel those out, we will have x is equal to the natural log of negative 2, or x is equal to the natural log of negative 3. Now there was one more example on here, and that other example gave us, what was it again? You have e to the x plus 6e to the negative x plus 5 is equal to 0, right? Equals negative 5, which is equivalent to adding 5 to both sides. So those two are equivalent. And here our problem is, wait, e to the negative x, what do we do with that? So that would be 1 over e, but we don't want it to be 1 over e. Instead, what I would like us to do is, what if we just multiplied everything by e to the x? Then don't I end up with e to the 2x here? And what's e to the negative x times e to the x? 1. So I left with a 6. And then here you have 5 times e to the x. But isn't this equation here just the same thing as this equation up here? So they might look different, but they are the exact same problem. Question? I believe, so technically here we could, so here we had the 6 times e to the negative x, and you multiplied by the e to the x, so you end up, yep, good clarification. Okay, I know that I did not leave with you with a lot of time. I would like to give you your homework though. On this first page, your homework is 7 and 8. And I'd like you to do 1. I think 1 is a good warm-up. 1, 7, and 8. On the second page, I would like you to do the first two, 19 and 20. That is your homework for today. I apologize for going long, but we needed to fit in a bit more so we can get caught up. That is all the material that we are going to be covering for today, so I'm going to stop our recording here.